Okay, so we're going to just go through basically introduction to complex numbers and kind of what we mean by complex numbers. So starting us off, we're going to just look at the square root of negative numbers. So we obviously know when any number is squared, the result is positive, but we can end up with situations where we need to find the square root of something, and under our square root we have a negative number. Now previously, if we kind of run into that, we would kind of write it off as I've done something wrong, I've made a mistake somewhere along the way, I need to go back and I need to change that. However, what we're seeing here is that that is not always a mistake. So in this case, the square root of -1 is going to be given a particular name, and we're going to call it I. And this is us introducing the notion of an imaginary number. Okay, so an imaginary number, and we represent by I. And this is kind of the key part here, the key part for this chapter. So I is the square root of -1, and I squared is equal to -1. That's kind of the key crux of these parts. So what we can do is we can use that then when we're finding the square roots of different negative numbers. So if we were doing the square root of 16, what we could do is compute the square root and add in an I part to represent that minus part. And where it comes from is that we could actually always split up a square root into a multiplication underneath the square root. So 16 multiplied by -1, and then we can actually separate those square roots out and we get 4i. But the quick way then is just to say for square root of say -144, we know the square root of 144 is 12, and we put an I there to represent that it was a negative 144 that we had. Same thing goes with the 8 here. Now with the 8 we have a little bit different, so maybe we will split it out because we can't get the square root of 8. We could rewrite it as the square root of 4 times 2, and that gives me 2 root 2 I. And the same thing kind of goes with the square root of 20 as well. If you were to type that into your calculator, square root of 20, we would get, let me see, can I rewrite it as a surd form? I get 2 root 5. So square root of negative 20, I would rewrite as 2 root 5 I. Okay. If we notice the powers of i's, then we can see a pattern. So when I start with I, obviously I is just I. When I have I squared, that's -1. That's from our definition. If we multiply by another I to get I cubed, that's going to be -I. If we multiply by another I, that's going to give me a kind of total then of +1. And then we repeat again. We repeat that kind of set of 4. So if we're asked to simplify a larger power of I, what we're going to do is we're going to divide by 4 and note the remainder. So depending on what remainder we have, that's going to tell us what the value is going to be. So let's look at an example of that. If I have I to the power of 10, 10 divided by 4 gives me 2 remainder 2, and that's going to mean that I have a value of -1. If we check back with our powers here, we have an I squared left over. What we're doing is we're really taking into consideration that I to the power of 10 would be the same as I to the power of 4 by I to the power of 4 by I to the power of 2. If you remember, multiplying would mean we add the powers. I to the power of 4 is 1, I to the power of 4 is 1, I to the power of 2 is -1. So I get an answer of -1. Same thing with I to the power of 35. If I divide 35 by 4, I'm going to get 8, remainder 3. And it's mainly the remainder that we're worried about, because the actual value itself is kind of, is all well and good, but it's really the remainder that we want to be looking at. And because it's remainder 3, we're going to be getting kind of I to the power of 3, I suppose. So I to the power of 35 is going to be -I. Same thing with 72, then 72 divided by 4 gives me 18 with no remainder at all, so it just has a value of 1. Nice even value. Same thing goes then with all of the powers we're looking at here. If we were to work out all of these values, we divide by 4, we compute what the result would be. So I'm going to leave some of these ones for you to do for yourself. We might just look maybe at one of them. So let's say if we look at this example here, the I to the power of 36. So 10I to the power of 36 minus 3I to the power of 57. Let's just compute those values. 36 divided by 4 is just 0, or is 9. Remainder 0, I should say. So divides in nice and evenly, which means I to the power of 36 is just going to be 1. 57 divided by 4 is going to give me a value of 14, remainder 1, which is going to mean that I'm going to have I. So I to the power of 57 is I. So I get 10 by 1 minus 3 times I, which is 10 minus 3I when we simplify it down. Okay, same thing happens with the last example here. What I'll say with this one is we need to compute the value on the inside first and then get the next power of that one as well. So I to the power of 19, if we divide 19 by 4, that's going to give me a value of 4 remainder 3, which would give me the same value as I to the power of 3, which is minus I. Then minus I to the power of 6 is going to give me a value of, see, minus I to the power of 6 gives me a value of minus 1. Okay, gives me a value of minus 1. So that means that I to the power of 19 to the power of 6 gives me a value of minus 1. Okay, so doing that inside one first and then computing the outside power. Okay, getting into the kind of nitty-gritty then of complex numbers. When we talk about complex numbers, they have a real part and an imaginary part. So we've already looked there and seen that the imaginary part is kind of represented by this I value. And our complex numbers are generally going to be written in this form, z equals a plus bi, where a is our real part and b is our imaginary part. Okay, so the kind of the coefficients there, I suppose, of just the a being our real part and then the coefficient of the I representing our imaginary part then. The complex conjugate, then our next thing that we kind of need to learn off, and it's represented by z with this little line over it, represents the reflection in the real axis. And to find the complex conjugate, we change the sign of the imaginary part. So the examples there, if z is 4 plus 3i, then z conjugate is 4 minus 3i. If z is 3 minus 2i, z conjugate is 3 plus 2i. Okay, so we're just changing the sign of the imaginary part. And worth noting there as well, we can kind of see we tend to use z for our complex numbers. Okay, and z conjugate then being the conjugate, obviously. And a note as well that for a complex number, if we multiply it by its conjugate, we end up with a real number. So looking then at some adding and subtracting of complex numbers, we add real parts with real parts, and we add imaginary parts with imaginary parts. So similar to kind of our algebra, think about adding your like terms. We can add similar things together. So we add anything that has an I to something else that has an I, and we add the numbers that are standalone, the real numbers, with the other real numbers. So we can kind of see that in these examples here. 3 plus 4 gives me the 7, 2i plus 6i gives me the 8i there. And same thing goes with the other examples as well. We add the real parts together. So 4 plus 7 here gives me 11. I take away I gives me a minus I there. Okay, only thing to watch out for with this last one is that you distribute that negative sign across to get minus 6 minus 2i. But then otherwise, following through in the same way. And if we're subtracting by a complex number, what I've said here is including a bracket is helpful, and we can see here why that is. So the question might be given as maybe z1, let me see, z1 take away z2. And if you were doing that and you were told those two values for z1 and z2, I would include a bracket there over around z2 when you're computing that. So just make sure you remember that that minus has to be distributed across all of those values. So let's just look at multiplying then. If we're multiplying by a real number, we just multiply the real and the imaginary part by our real number, okay, as we'd expect. If we're multiplying a complex number by another complex number, we apply the same way we would with algebra. So same as we've done with kind of adding and subtracting, we're treating it with the same rules we would with algebra, remembering that I squared is minus 1, because if we multiply two complex numbers, we're going to have an I squared term. So let's see how this works here. If we have z1 multiplied by z2, that's 3 minus 2i multiplied by minus 4 plus 5i. So multiplying it the same way we do with algebra, that gives me minus 12 plus 15i plus 8i minus 10i squared. Now let's note as well that I squared is going to be minus 1, which means that this altogether would just become plus 10. And then simplifying and adding anything together that we can, we end up with a value of minus 2 plus 23i. Minus 2 plus 23i. Okay, looking at the next example that we have here, then 3z1, we're just multiplying by a real number here. So 3 multiplied by 3 minus 2i gives me a value of 9 minus 6i. So just multiplying each part by 3 there, as we would with algebra. You're nearly treating that I as if it's an x value, just remembering that if we end up with an I squared, we don't leave that, we rewrite it as -1. So all our complex numbers should just have an I part, no I squareds or any higher powers of I. Looking at this part here, then 2z1, so 2 times 3 minus 2i minus 4z2, filling in those values, multiplying out 6 minus 4i plus 16 minus 20i. And again, simplifying as best we can, we get 22 minus 24i. Okay, so as I say, just applying it the same way we would if we were multiplying terms in algebra. Okay, we've some practice questions there. Again, the same idea applying with each of these questions here. So you're just following through, applying the same rules. If you're multiplying by a real number, you're multiplying across. If we're multiplying two complex numbers by each other, we just need to be careful about that I squared term. So we're going to look then at dividing, because dividing is a little bit different because we have an extra step to worry about, or not to worry about, but just to consider. So when we're dividing a complex number by a real number, we would divide the real number into each part of the complex number. So say we had 2 plus 4i and it was divided by 2, we would divide the 2 into each part, which would give me 1 plus 2i. If we're dividing one complex number by another complex number, this is where we have to make use of our complex conjugate. So remember, that was the number where we changed the sign of the imaginary part. And what we do is we multiply the numerator and the denominator by the complex conjugate of the denominator of the bottom part. So multiply top and bottom by the conjugate of the bottom. And this is going to give us a real number, which can a lot of the time be divided in. And then that leaves us with a nice complex number in a plus bi form. If it does not divide in, we still need to write out our complex number into that a plus bi form, just to keep it consistent with what we're asked for, I suppose, in the question. So let's have a look at a few of these examples here, and then I can leave the practice questions for yourselves. For the first one, we've already kind of said we divide this 2 part into each part of the complex number, which gives me a value of 2 plus 4i. Okay, for the second part here, we are going to be multiplying top and bottom by the complex conjugate of the bottom part. And the complex conjugate of the bottom part is 3 plus 7i. So now we multiply out, we get 18 plus 42i plus 6i plus 14i squared. And that's all over 9 plus 21i minus 21i minus 49i squared. Okay, simplifying down as best we can, 18 plus 48i minus 14, that becoming minus 14 because of the I squared there, and then doing our part on the bottom here, that becomes a plus 49. So I get 18 minus 14, which is just 4 plus 48i over, let me see, 58. And then we can't really simplify that down anymore. So the only last thing we can do is just to split it out into two fractions, because we don't want to rewrite it as one whole fraction. We want it in that a plus bi format. So we would write it as 4 over 58 plus 48 over 58i, separating it out into two fractions there. Okay, same thing applies with this second example here, 2 plus I over 8 plus 2i. We would multiply top and bottom by the complex conjugate of the bottom part, 8 minus 2i. Following that through, 16 minus 4i plus 8i minus 2i squared over 64 minus 16i plus 16i minus 4i squared. So 16 plus 4i plus 2, that plus 2 coming from the minus 2i squared, because we remember that I squared is the same as minus 1, and the plus 4 coming in there, we get 18 plus 4i over 68, and again we can split that out. And simplifying those fractions if we can at all, I think to simplify down 9 over, let me see, 34 plus, let me see, 2 over 34, 1 over 17. 2 over 34, 1 over 17. Okay. With the last example here, we're applying the same idea. We're going to multiply top and bottom by the complex conjugate of the bottom. The complex conjugate is where we change the sign of the imaginary part, so we're multiplying top and bottom just by I. We get 9i minus 2i squared over minus I squared. That gives me 9i plus 2 over minus 1, or minus minus 1, so plus 1. Rid of that there. So we get 2 plus 9i as our end result for that one there. Okay, so I'm gonna give those practice questions for yourselves to do. Okay, so we're not going to go through any of those ones there. There's really nothing different with those ones compared to the ones we've just done. What we'll look at now is the last little part in this section, and it's that idea of equality. So we've looked at this a little bit when we would have done identities back in algebra 1. Back in algebra 1, we would have done the same kind of idea here. So for two complex numbers to be equal, we say that the real parts must be equal and the imaginary parts must be equal. So if we're given two complex numbers, we can compare the real parts and we can compare the imaginary parts, and that's going to allow us to make some calculations and to make some I suppose, to work out some unknown values in the questions. So say we look at this question here, we want to find x and y if 4x plus 7yi minus 2 times 2 plus 3xi is equal to 8 minus 4i. So what we're going to do is we're going to try and simplify this left-hand side. So we'll start by multiplying out that bracket, giving me minus 4 minus 6xi. Then let's try and group together anything that has and doesn't have an I part. And then the last thing we can do would maybe just be to factor out that I part and group together the things in front of the I on the left-hand side. We're going to be comparing this with what we have on the right-hand side. So starting first of all with just the real parts. So we can say that 4x minus 4 must be equal to 8. So 4x must be equal to 12, so x must be equal to 3. Then comparing the imaginary parts, same thing again. 7y minus 6 times 3, we can fill in the value for x that we have found out. Minus 4, 7y equals 14, so y must be 2. So comparing the real and the imaginary parts there just allows us to work out that value then, and those values for each of those for x and y in the question there. There's another use for this equality idea, and it's when we're finding square roots. So when we're looking at a question like this, they've said that the square root of 5 plus 12i can be written in the form a plus bi. So if we just lay out exactly what they've said to us there, they've said that this square root can be written as a plus bi for some a and b. So this is how we're going to start our question. Now we just need to follow through. So let's try and square this left-hand side here to eliminate that square root. That's going to give me 5 plus 12i. It's going to give me a squared plus 2abi plus b squared I squared, so not forgetting the I part there as well. We get a squared plus 2abi minus b squared, and we can straighten up this right hand side as a squared minus b squared plus 2abi, and on the left hand side 5 plus 12i. So as we've done with the first part, let's just start by comparing the real parts first of all, and we get that a squared minus b squared is equal to 5. If we compare then the imaginary parts, the 12 and the 2abi, we get that 2ab is equal to 12. What we need to do at this point now is we need to work out a value using one equation that we can sub into the other equation. So the best thing for us to do is to start with one of the smaller equations. So say we start with this equation here, and we'll find a value for b. So we could say that b is the same as 6 over a. Then instead of b over here, I'm going to sub in that value that we found, 6 over a. Continuing that out, I get 36 over a squared equals to 5. I can multiply across by a squared there to get a to the power of 4 minus 36 equals 5a squared. A to the power of 4 minus 5a squared minus 36 is equal to 0. I need two numbers that multiply to give me 36 but add to give me 5. And noting as well that in here, instead of x, we're using x squared because this equation is in a to the power of 4 and a squared. We're using a squared in the center there as well. So separating these out, we get a squared equals 9, which means that a is going to be plus or minus 3. And we can also say that a squared could be minus 4, which would make a plus or minus 2i. But by definition, a has to be a real number. So this part is not allowed. A has to be a real number by definition. So we know that a is plus or minus 3 now. So if a is 3, that would make b 2. And if a is minus 3, that would make b minus 2. So my two numbers are 3 plus 2i and minus 3 minus 2i. So just by comparing and setting up the equation as they've set it to us in the question, we can find out the value of this number z, the square root of the complex number that we're given. And we have two potential answers that we could have. So we look at one of the exam questions here. So looking at the second exam question, we have a very, very similar to the example that we have. So I think we're going to work through maybe the first exam question. So it says, or the first practice question, I suppose, here of the exam style. So determine the values of x and y that satisfy this equation. So let's try and work out these values. So again, we start with the left-hand side. And we're going to tidy this up, being careful with that minus on the outside there, that we just kind of include that in all the parts, and the I on the outside also, that we include that in all parts there. So tidying up now as well, just everywhere that I have kind of an I part, I'm going to combine those together. So I get 3y minus 2 minus 5xi in total. And on the right hand side, it's 10 minus 6yi. So same as we've done already, comparing real and imaginary parts. So 4x is 10, which means x is 5 over 2. So 10 over 4 or 5 over 2. Comparing then imaginary parts, we're going to get that 3y minus 2 minus 5x is equal to minus 6y. We can sub in the value for x that we've just worked out, which is 5 over 2. So we get 3y, let me bring the y's across here as well, to give me a total of 9y minus 2 minus 25 over 2, and we'll have that equal to 0 for the moment then. So let's just use our calculator here to save ourselves some trouble. We're going to just add these two, 29 over 2 on this side here, and then I can divide by my 9 to get my value at the end there of 29 over 18. So an unusual value, but still correct for this question here, because we've applied everything in the correct way. We're going to look then at part 2, which is one of the equality ones for the square root that we just looked at. So we start by laying out the question. So we're saying that the square root of 9 minus 40i is the same as sum a plus b. We're going to square both sides, which is going to give me, same as we've had before, a squared plus 2abi minus b squared. So I'm skipping a little step there, remembering from our example we would get b squared I squared, which is the same as minus b squared. So now just kind of grouping things together to make everything as clear as possible for ourselves, we have a squared minus b squared plus 2abi. So let's just compare real parts first of all. So we would get a squared minus b squared equals 9, and we would get 2ab being equal to minus 40 when we compare the imaginary parts. So let's work out those values. If we find a value for b, we could call it minus 20 over a, and we could then sub that in for b here. Going to be squared. So a squared minus 400 over a squared equals to 9. We get a to the power of 4 minus 400 equals 9a squared. And again, bringing that over, minus 9a squared minus 400 equals to 0. So we want two numbers that are going to multiply to give me 400, but will add to give me 9. Those two numbers are going to be 25 and 16. 25 and 16. Okay, 1 plus, 1 minus. So we get that a squared is 25, which means that a could be plus or minus 5. And the same thing happens here as happened in the last question. We get that a could be plus or minus 4i, but a has to be a real number. So it's not allowed to be 4i. And the same thing would happen if we had gone for b as well. Even though we have bi, b itself has to be a real part. We can't have 2i, okay? So taking that there, if a is 5, that would make b minus 4. And if a is minus 5, that would make b 4. So my two answers are 5 minus 4i or minus 5 plus 4i for my two answers. So a lot kind of gone through there. General idea of what a complex number is, the idea of those powers of I and how we kind of work around those and kind of grapple with those, I suppose. Adding, subtracting, multiplying your complex numbers and kind of following the same rules as we have with algebra. Dividing using our complex conjugate, so that being the changing the sign of the imaginary part. And then this idea of equality and how we can use that to compare left-hand side to right-hand side by comparing the imaginary parts and the real parts on either side, and how that should be the same if those two expressions are going to be equal. So all of these things are really, really important for when you're looking at complex number questions. It's really important that you have that foundation and are able to pull on that then when you're answering the later questions.